Chapter 7, Sedimentary Rocks. The importance of sedimentary rocks. Sediments and sedimentary rocks cover approximately 75% of the Earth. They comprise about 5% by volume of the Earth's outer 10 miles. They contain evidence of past environments. Sedimentary rocks are an important resource. Coal, oil, other fossil fuels, and groundwater resources can be found within them. Origins of sedimentary rocks. Sedimentary rocks are products of mechanical and chemical weathering. Sediments and soluble constituents are typically transported downslope by gravity. These sediments are then deposited and subsequently buried. As deposition continues, the sediments are lithified into sedimentary rocks. There are three types of sedimentary rocks: detrital, chemical, and organic sedimentary rocks. Detrital sedimentary rocks form from sediments that have been weathered and transported. The chief constituents of detrital rocks include clay minerals, quartz, feldspars, and micas. Particle size is used to distinguish amongst the various rock types. Okay, if you have particles of about 2 millimeters in diameter, those are your sand grains, so they'll form your sandstones. Smaller particles will form your siltstones, or mudstones, or shale, and larger particles are going to be your conglomerates and your breccias. Shale. Silt and clay-sized particles make up shale, formed from gradual settling of sediments in quiet, non-turbulent environments. So like the bottom of a lake, where the water isn't moving around. Sediments form in thin layers called laminae. Has facility, meaning the rock can be split into thin layers. Crumbles easily and tends to form gentle slopes. It's the most abundant sedimentary rock. It's a picture of shale with some fossil remnants in it. Sandstones made from sand-sized particles forms in a variety of environments. It's the second most abundant sedimentary rock. Quartz is the most abundant mineral in sandstone. Quartz sandstone is mostly quartz. Arkose sandstone has a large amount of feldspar. Greywacke contains rock fragments and matrix in addition to quartz and sandstone. Here's a picture of quartz sandstone, and here you see a close-up, see the little sand grains. Quartz are in there. The particles of sandstone vary and are classified by their sorting and shape. Sorting is the degree of similarity in particle size in a sedimentary rock. If all the grains of a rock are similar size, the rock is well sorted. If the grains in a rock are of different sizes, both large and small, the grain is poorly sorted. Sorting can help decipher the depositional environment of the rock, or what kind of environment did this rock form in. Okay, particles of sandstone also are classified by their shape. Particle shape varies from rounded to angular. The degree of rounding is indicative of how far the sediments have been transported. Rounded sediments are typically transported great distances, while angular sediments are only transported a short distance. There's more opportunity for mechanical weathering to occur while a sediment is being transported. That's why those that travel farther are more round. Okay, so in this diagram, we go from very poorly sorted sediments of all different sizes. They gradually become very well sorted, all the same size. Then for the shape, highly angular, not very spherical, and gradually becomes rounded, or really smooth. Conglomerate and breccia. Conglomerate consists of rounded gravel-sized sediments, and breccia consists of angular gravel-sized sediments. Both types of rocks are poorly sorted. So a picture of a conglomerate, nice rounded gravels in there. And here's a breccia, very angular pieces of rock in there. Chemical sedimentary rocks form from precipitated material that was once in solution. Precipitation of material occurs by inorganic processes such as evaporation, or organic processes from water-dwelling organisms that form biochemical sedimentary rocks. Limestone is the most abundant chemical sedimentary rock, mainly composed of the mineral calcite. Can form from inorganic and biochemical origins. Biochemical limestone originates from the shells of marine organisms. Large quantities of marine limestone are formed from corals. Corals secrete a calcium carbonate skeleton and create reefs. So Australia's Great Barrier Reef is the largest coral reef on Earth. Coquina is composed of cemented fragments of shell material. Chalk is composed of the tests of or skeletons of microscopic marine organisms. Okay, so here's pictures Australia along the shores where the Great Barrier Reef is. So there's a nice aerial view of a portion of the Great Barrier Reef. Now, this is a picture of a basically antique barrier reef up at the Guadalupe Mountains National Park in Texas. So this is a very ancient Permian age reef. This complex, this is a lot of limestone. Picture Coquina, so it's cemented shell fragments. White chalk cliffs. Here's some nice white chalk cliff form hard parts of microscopic marine organisms. Here's a group of coccolithophores. Okay, so they scan the electron microscope. Okay, so you see the scales that make up the hard parts of that microorganism. Coccolithophores are one-celled marine plants with plankton that live in large numbers. Okay, and they bloom offshore of certain coasts. So here's a nice plankton bloom. And they will eventually, millions and millions of these will form chalk. Limestone, again. Inorganic limestone forms when chemical changes increase the calcium carbonate content of the water until it precipitates. Travertine is a type of limestone found in caves. It's precipitated when water in the cave loses carbon dioxide. Okay, so if you heard stalagmites and stalactites, which are like rock icicles in a cave that form, the stalactites from the roof, and the stalagmites from the ground, that rock those stalactites and stalagmites are made of is travertine. Oolitic limestone is composed of small spherical grains called ooids. Ooids form as tiny seeds and roll in shallow marine water supersaturated with calcium carbonate. Here are some ooids. Okay, and there's a limestone formed from these ooids called oolitic limestone. Dolostone, similar to limestone but contains magnesium. Origin of dolostone is still unclear. Significant quantities of dolostone are created when magnesium-rich waters circulate through limestone. Chert is composed of microcrystalline quartz, forms when dissolved silica precipitates out. So flint and jasper and agate are varieties of chert. Here are some pictures of chert. There's a chunk of flint, some jasper, nice agate, some petrified wood. Okay, so water percolated into this log and slowly solidified, quartz solidified into the wood, making this petrified wood. Arrowhead, you can probably made out of flint. Evaporites, another chemical sedimentary rock. The evaporites form when restricted seaways become oversaturated and salt deposition starts. Rock salt and rock gypsum are two common evaporites. Occasionally, evaporites form on salt flats when dissolved material precipitated as a wet crust on the ground. So here is a nice salt flat. Okay, salt flats, Bonneville salt flats, or here in Utah. Okay, and it's a place that's so flat that in the past we tested cars and other vehicles for speed out there. Organic sedimentary rocks form from carbon-rich remains of organisms. Occasionally, plant structures, leaf, bark, and wood are identifiable in coal. So an organic sedimentary rock coal is an organic sedimentary rock. Okay? So common chemical sedimentary rocks. Coal is different from other rocks. This is composed of organic material. Stages in coal formation. You have plant material, okay, and like a swampy area, lack of oxygen. As the moisture starts to be compressed out of it, it becomes peat. As more pressure and removal of moisture, the peat becomes lignite. And more and more pressure, it becomes bituminous coal. And then if it becomes metamorphosed, it becomes anthracite. Okay, so large amounts of plant remains need in an oxygen-poor environment like a swamp. Bacteria partially decomposes the plant matter. Bacteria die due to the acids released by the process, and now what remains is peat. Temperature and pressure over time make the peat change into lignite coal. More pressure and temperature, lignite becomes bituminous coal. Lignite and bituminous coal are sedimentary rocks. More pressure and temperature, bituminous coal becomes anthracite. Anthracite is metamorphic. As more water and volatiles are compressed out, the more the proportion of fixed carbon is left. The more carbon, the higher the energy rating. Okay, so more energy you can get out of that coal. So nice diagrams. We have our swampy environment. As the remains get buried with compaction, it becomes peat, and then more compaction and pressure, the volatiles get pushed out, water gets pushed out, comes lignite coal, which is a nice rock. More compaction comes bituminous coal, and eventually it can be metamorphosed and become anthracite coal. This lignite is still a very soft rock. You can break it apart in your hands. Okay, the bituminous is much harder. Anthracite's a pretty nice hard rock. Okay, turning sediments into sedimentary rock, diagenesis and lithification. Many changes occur to sediment after it's deposited. Diagenesis, chemical, physical, and biological changes that take place after sediments are deposited and buried. This occurs within the upper few kilometers of Earth's crust. Examples are the recrystallization of more stable minerals from less stable ones. Example, aragonite to calcite. Many changes occur to sediment after it's deposited, so also lithification. Unconsolidated sediments are transformed into sedimentary rocks by compaction. As the sediments are buried, the weight of overlying material compresses the deeper sediments. And cementation involves the crystallization of minerals among the individual sediment grains. The moisture that's in there may have some minerals in solution. As they precipitate out and crystallize, they actually glue those sediments together. Okay, now sedimentary rocks are also classified according to the type of material they're made of. Okay, so there are two major groups, were the detrital, and the other one was the chemical along with the organic. The detrital we call a texture clastic, composed of discrete fragments cemented together. And chemical and organic we call non-clastic or crystalline texture, where the minerals form patterns of interlocking crystals. So here's our chart for identifying sedimentary rocks. This column here is the detrital, and over here is our chemical and organic. And you see on this axis we have our size of grains. So this is our sand size grains, make arkose and sandstone. Our coarse grains are our gravels. Our gravel size form our conglomerate if they're rounded, breccia if they're angular. Fine size grains make our siltstones, and very fine are shale or mudstone. Now the chemical and organic, if it's made of calcite, then we can get our crystalline limestone or a travertine. If the biochemical ones, limestones like made of shells or coquina, fossiliferous limestone and chalk. Now if it's made of quartz, okay, it's precipitated out of water, we get our chert or flint or jasper and our agate. If it's evaporate that's made of gypsum, be rock gypsum, or salt or halite, be rock salt. And then our altered plant fragments make our bituminous coal. Okay, sedimentary rocks represent past environments where those sediments were deposited. An environment of deposition or sedimentary environment is a geographic setting where sediments are accumulating. This determines the nature of the sediments that accumulate, the grain size, the grain shape, etc. Types of sedimentary environments. There are three broad categories: continental, marine, and transition. Continental environments are dominated by stream erosion and deposition. Streams are the dominant agent of landscape alteration. Glacial. Deposits are typically unsorted mixtures of sediments that range from clay to boulder size. Wind or aeolian. Well-sorted fine sediments. Marine environments, shallow marine up to about 200 meters, borders the world's continents, receives huge quantities of terrestrial sediments, terrestrial from the land. Warm seas with minimal terrestrial sediments have carbonate-rich muds. Deep marine, okay, seaward of the continental shelves, primary fine sediments that accumulate on the ocean floor. Turbidity currents are the exception. Now, transitional environment. The shoreline is a transition zone between marine and continental. Examples are beaches, tidal flats, lagoons, and deltas. Here's just a diagram of where some of these environments are and what they look like. And it's probably also in your textbook for a closer study. Like here's a beach, it's in a transition zone. Here's estuary, be also in a transition zone. Deep marine environment. Okay, so here's alluvial fan, so terrestrial. Okay, get the idea. Sedimentary facies. Different sediments often accumulate in adjacent environments. Each unit, facies, possesses a distinct set of characteristics reflecting the conditions of a particular environment. Transitions between the different facies are typically gradual. So beach-like sediments may gradually change into an offshore sediment and then to a deep marine environment sediment. So here we have our sandstone facies from our beach, and it's going to gradually change into a shale facies and then gradually change into a limestone facies. This provides additional information useful in interpreting Earth's history. Types of sedimentary structures we may see. The layers of sedimentary rocks are called strata or beds. Most characteristic of sedimentary rocks. Bedding planes are lines that separate the strata. So here we have strata. These are strata, the layers, and the bedding planes are the lines between the layers. Types of sedimentary structures include cross-bedding. This occurs when the layers in a sedimentary rock are inclined, characteristic of sand dunes, deltas, and some stream deposits. So here, let's say the sand was deposited, the wind was traveling in one way, and then it was deposited, the wind traveling in another way. Okay, and then the wind was traveling another way. So over time, as primary wind direction changes in an aeolian or wind environment, the sand dune is going to be growing in different directions. So then you have cross-bedding, the different angles between the different layers. Graded beds are a unique situation where sediments and strata gradually change from coarse at the bottom to fine at the top. We often associate these with turbidity currents. Okay, so here's our continental shelf, and our continental slope is the steep area, and then there's these subterranean caverns coming off that shelf. And turbidity currents are a rapid movement of water mixed with all kinds of types of materials flowing down this canyon and then depositing this mixed up material down here. But this material gets graded with the larger particles to the bottom to smaller particles. Other sedimentary features you may see: lithified in rocks are ripple marks, so small waves. Lithified in sedimentary rock. Mud cracks indicate sediments that form in an alternating wet and dry environment. Fossils are remains of prehistoric life. I actually even have a sample of raindrop imprints preserved in rock. But here is some ripple marks. Here's some mud cracks. Well, here's a fossil trilobite. And here's some dinosaur footprints. The carbon cycle in sedimentary rocks. CO2 is one of the most active parts of the carbon cycle. Plants absorb CO2 through photosynthesis. When plants die, some of the CO2 is deposited in the sediments. Over geologic time, considerable amounts of plant biomass are converted to fossil fuels. When fossil fuels are burned, that CO2 is released back into the atmosphere. That's the end of the